Oh, you didn't? Okay. So you're Giuseppe?
What?
Your name is?
Yeah. I just got into the contract.
Yeah, it's okay. There's actually someone was sitting there, but I guess they could.
I'll just.
Yeah, pull that seat around so he can sit in the end if he wants. Okay, so I made a minor tactical error. I didn't bring the book with me, but if there are any questions about any of the homework, you could ask them now or come to my office hours. If you want to turn it in, you can just sometime, you don't have to do it now, but, at the break or afterwards, you could just pile up anything on my desk. I mean, on this desk. I'm trying this thing out. The balances between some people with quiet voices in the back who I'm not going to hear very easily unless they speak up. And the other side is with this thing, I like hear like the little, like someone in the back, like scratching their arm, So I don't know. We'll see. I'll try it without it for the moment. See how that works. My problem with hearing is more distraction. Like if everybody's quiet, I can usually hear pretty well. If there's murmuring and whatever, it kind of drives my brain crazy. Okay. I just jump in or... Well, this neighbor of mine, he's very friendly. He likes to give me gifts. And he gave me this thing yesterday. It was a can of Monster Energy drink. And I thought, at 2 in the afternoon, what could go wrong, And I didn't drink the whole can. I put it in a container and had a little bit. And there I am at 3 in the morning. I went to sleep for a few hours, and then it was like, it's keeping me up. And come in. Your seat is awaiting. Is Devin here? Devin is not here. Okay. I was thinking about something that I'm a little obsessed with, and I don't want you guys to be obsessed with. But I can't really talk about it without saying something about it. So it has to do with limits. And, we've talked about limits where you have some function, some f, and there's some point c, and we want to know, we want to know what it's getting close to. And we've done all that. We've gone over that. We have a very specific, ugly mathematical definition to define what that is. But then, we have maybe this function ends here. We have some endpoints. And there is such a thing as a kind of a one-sided limit, right? So, I don't know, let's call that, L, and we'll call that H. And we can have a limit, the limit as x approaches L from the positive direction of f. And here we can have the limit of x approaches h from the negative direction from the negative side of f of x. And I'm obsessing about this, and I don't want you to worry about it, because when it comes up, I'm just going to hand wave. This is not, math degree analysis. It's just not that important. But I was thinking, why am I obsessing about it? It's like, well, at some point in my life, I got a math degree. I'm one of those guys who likes that kind of stuff and real, knows, like, let's examine something really close, which we're going to do in a few minutes. That's the subject matter. I guess I should just write it up here. Continuity. We'll get into what that is and what that's all about. But it got me thinking a lot about how, we have different people in here. Everybody's different. Everybody has their own personality. There may be some similarities, like some of you may be, adventurous or, very socially conservative. I don't mean that in a bad way. You want to find someone, hook up with a partner, have kids, have a house with a picket fence. That's fine. We all have different personalities, and yet, those personalities are going to fit with where we're going or not, right? And yet, everybody here, I think, already has picked a major. Now, you can pick a major, you can change your major, but isn't it a little early? Shouldn't you, have a year of college first? Find your way around, think about it. I couldn't sleep, so that's what I was thinking of. It's unimportant. All right, I just threw that out. Let's talk about. Last chance for the moment. Anybody want to ask a question about any of the homework? Hey, yes.
So the thing that we're talking about, going to the left and the right, for example, let's say that at that limit right there, it's an open circle.
Well, it could be, or it might not. It doesn't matter what it is here. And for these, it doesn't matter what it is here. As far as
they ask us, the limit comes from the right, the left, the limit comes from the left. There will be something there, but what would we put if it was just asking what is f of x at that point? The view does not exist right now.
I think that's exactly what we're going to be talking about today.
Oh, that was my homework.
Okay. But just, again, to just clarify, for a limit, you've got to be able to approach it from both directions. For a one-sided limit, you're just approaching it from one. And that's all you need to know. You don't need to know the definition. It's similar to the definition of a limit. Yes?
I felt like the homework kind of jumped the gun a little bit on, as far as what we talked about in class.
Yeah,
I've done some calculus.
and I agree with you.
Okay.
All right? Don't be, if you want to wait before you turn it in, that's fine.
Okay.
I did a little, and it was a mistake, and I'm going to be more careful.
Okay, cool.
But mea culpa.
No worries. I just wanted to.
Okay, no, you're right. There's some questions where it's like, well, if you've taken calculus, you've seen it. You could have looked back in the book a little and figured it out. But really, I shouldn't have jumped the gun on that. Okay. Anything else before we jump into this meaty topic? Again, I'm going to digress for a second. You guys are young enough that you may or may not have had this in your life. Has anybody here gone out to a fancy restaurant? Somebody else is paying, hopefully, and you get the menu, and maybe you don't know what to do because it's the first time, or maybe you have a natural intuition. My intuition is I go and look for the main course. See, what is on here that I'm going to like and I'm going to feel satisfied with? And then once I've picked that, then I'll kind of go back and look at, well, what are the appetizers? You know, the soup, the salad, maybe there's some fancy fish dish or, you know, chips or whatever it is. And that's because, you know, maybe I'll like the appetizer, maybe I won't. But if I have the main course and it's kind of satisfying, I'll go home happy and hopefully not with too much indigestion. Now, what does that have to do with anything? Well, we've already talked about limits. It seems a little obscure. Yeah. And today we're going to talk about something called continuity. And these are kind of the appetizers, right? What we're really going to talk about a lot in this class is finding derivatives. And I'm going to talk to, that may seem a little odd. We're going to talk about why this class is mostly about derivatives. But I just want to be clear. This is, again, we're kind of, we ordered some challenging appetizers here. They maybe don't care for it. You just have to get the feel for these things. The real work is going to be derivatives. You're going to have to memorize some stuff somehow, either by doing or, there'll be some formulas. But I don't want you to panic because, again, this is a little obscure. Maybe not. Maybe it'll feel good. Maybe you've taken calculus before and you're all cool with it. So, in everyday language, continuous means something that goes on without interruption. Now, something that continues, right? Your continuing education, straight from high school to college. Well, there's this break in between. In math, in calculus, we're talking about some kind of function that approximately it means that, well, you could draw that function without taking your pencil off the paper. I mean, the drawing is just a drawing. It's not the actual line or the curve. But that's one way to think about it. There are no holes in this. Now, in a way, this seems intuitive, and it isn't. Because in the real world, nothing is like this, right? Nothing is, the blackboard feels smooth. It's continuous. But in fact, there are little tiny holes in it. Gazillions of them. Because it's just made of atoms. But in math, we're talking about a line that, every point, there's a number. Between every point, there's more numbers. In fact, it's kind of weird. You could take two very, very close together points and just look at all the points in between. And there's not only an infinity of them, there's an uncountable infinity of them. It's just really weird stuff. There's as many points between 2 points, say on the curve, as there are in a line that goes off to infinity. Very strange. And again, continuous means that there's no breaks in that. There's no holes in that. Now, because this is math, we have to be very precise about what we're talking about. And so we're actually going to be talking about, we're going to use the word continuity in 3 different ways. The first is going to really give us a running start, is continuity at a point. I'll just leave that here for the moment. So we have a very precise definition in math for continuity at a point. You got to let it seep in a little, grow on you, and then it'll be like, oh, yeah, it kind of makes sense. All right? So we're going to say f, some function is continuous. I'm going to abbreviate at a point C if and only if, and here we're going to go back to our limits. If the limit as x approaches C of f of x is equal to f of C. So if we have some function and we're looking at some limit here, as we get close, we have a limit. There's a point, some value, some limit. It doesn't matter what the function is defined there for it to be a limit. But we're saying if the limit just happens to be the value of the function evaluated there, then we are continuous at that point. You really have to dream about that a little. Why is that? It's like, I guess you could say, there wasn't a hole here, right? It could be discontinuous. The function could be defined up here, and there's a little hole in it, and it's not continuous. Okay, so in particular, there are three things we need for f to be continuous at a point. F of C has to be defined. C has to be a member of the domain of f. The limit has to exist. It has to have some limit L. And L has to equal f of C. So 1, 2, 3 things required to be continuous at a point. Now, we're going to get back to some more continuous things, but we want to talk a little bit about functions that aren't continuous at some point. We want to categorize them a little. So this is discontinuities. So my first example looks like this. You have some function, and then at some point C, it just jumps from one place to another. Now let's see why that fits this definition, or it doesn't fit this definition. Well, we could have something like this, where it's not defined up, this is kind of a hole, and this is where it's defined. Well, sure, f of C is defined. C is in the domain of f. But we don't have a limit. Why don't we have a limit here? We have a left-handed limit that brings us down here. I'm sorry, this is the left-handed limit. This is the right-handed limit. Why is it not a limit? I heard that from somewhere. They're not the same. That's right. So this is called a jump discontinuity. That's one kind of discontinuity we run into. Next, we have a function. I think we brought something like this up before. It's a very strange function that mostly comes up to scare us or annoy us from time to time, like does weird things. F is 1 if x is rational. In other words, if it's the ratio of a and b where b is not equal to 0, or a and b are real numbers. But it's 0, x is irrational. Okay, what does that look like? Well, I guess we shouldn't even have the axis here. We'll draw it kind of like this, but that's not really what it looks like. I mean, these points at 1 are so close together we can't see any holes in between. The rational numbers are what we call dense. Between every rational number there's another number, another rational. And the irrationals are down here. Well, if we pick some c here, it's either going to be 0 or 1, but there's no way that there's a limit here, right? For a limit, as you get close, you have to get closer to the limit. If there's a limit at c, you have to get closer to the limit as you get close to c. But here, this thing is like jumping up and down like crazy. This is what we call jump discontinuity. This is discontinuous everywhere. Now, we won't see this very often. There's actually there's a graduate level course where you're studying real numbers. And you actually do calculus on weird functions like this, but we don't have to worry about those. Okay, finally, we might have a function that kind of looks like this. It's got a little hole in it, and well, it's defined at c. This is f of c, and it has a limit, which is down here, which is some other value. It's not f of c. It's f of close to these values, and it's a discontinuity, but it's a special kind of discontinuity. This is called a removable discontinuity, or it's a fixable discontinuity, if you like. The idea is all we have to do to make this point, make it continuous, the function continuous at this point, is redefine f of c to be here. Now, I guess there's another category like this that also fits this definition. Maybe this point isn't even defined. So if I had, say, x squared minus 1 over x minus 1, and c is 1. Well, it's not defined here, but if we do our trick, we make this x plus 1, x minus 1 over x minus 1. We see this has a limit of 1 and this has a limit of 2, so this is going to have a limit at 2. If we redefine f of 1 as 2, we've removed the discontinuity. So those are three types of discontinuities. There's one more. I guess I guess I can. No, I'm just gonna erase this. let's look at the function f of x. I think we looked at this before. 1 over the absolute value of x. Kind of goes like this and over like this. So as we get close to 0, this just increases beyond bound, as does this. This is called a discontinuity at infinity. There's no way you can, obviously there's no way you can draw this, right? You have to reach pretty high to infinity. And the function does not, it's interesting. You can get as close as you want, but you can't reach that point. Okay, so so you should be aware of the different kinds of discontinuities, be able to identify them, and I think realize that this kind of discontinuity, with a little hand waving, we can fix it. The other discontinuities we can't. All right. Any questions about that so far? We're gonna do a couple examples. Okay. It might help if you had some paper to write this down. Let's take a look at this. F of x equals x squared minus x minus 2 over x minus 2. And we want to know, is this continuous at x equals 2? Actually, let's ask it a little different. Where is it continuous? Well, any thoughts, any ideas? Yeah, it's discontinuous here. What about everywhere else? Is there anywhere else it's not continuous? Well, anywhere else, you plug in, you're going to get a over b. You're going to get a fraction. As you get close to that point, you're going to get closer to this fraction. The limit, as you get close to that point, is going to be the function at that point. So everywhere else, it's continuous. All right, we're going to take this and we're going to just modify it a little. We're going to say f of x is equal to this. If x is not equal to 2, and it's equal to 1 if x equals 2. What about now? Any thoughts? Is this function continuous at x equals 2? Well, okay. Let's take a look at the definition. What's the limit? X squared minus x minus 2, where x minus 2 as x approaches 2. Well, okay. Do we remember how to factor? Now, I'm sure you're all quiet because you're just focusing on the difficult details here, but I just want to say, if you've forgotten how to factor, come see me. You're going to need this, right? I assume that's not the case. So we're going to use the simplest version we can, right? Okay, so we need a plus and a minus, and we want this to be minus, right? Does that do it? Get 2x, minus 2x, and plus 1x. This is 1 minus x. The minus 2, I already got the x squared. Okay, good. All right. But this is the limit of times the limit x minus 2, x minus 2, x minus 2. Okay. And this limit is 1. And this limit is what? Oh, huh. Maybe I wrote the problem down wrong. How about now? Does that look better? Now this is a continuous function. Okay. What if I change this a little? I say, hey, this is 1 over x squared. Guess I'm going to have to adjust this. For x not equal to 0, but 1 for x equals 0. So we want to know, is this continuous at 1? What does this look like anyway? Well, it's 1 here. Oh. As x gets large, this goes to 0, right? And as x gets small, it gets very large, okay? And since it's squared, it's symmetric. Well, okay, this is simple. The limit doesn't exist as you get close to 0. So this is discontinuous at 0. Okay. Yes. Here or here? I'm sorry? Before I added this, it was discontinuous. But when I add this, right, my limit as I get to 2 turns out to be 3 times 1 is 3. So having fixed it, this was a removable discontinuity. Having removed it, it's now a continuous function. Yes? I think you said you think I made a mistake, and you're probably right, because I'm up near the blackboard, but I didn't understand what did I do wrong?
When x equals 2, the f(x) should equal 3, and then that makes it continuous.
That makes it continuous, yeah. See, the limit is 3. Oh, you know what? Yeah, and I've just defined f of 2. Oh, you're right. You see? One person's paying attention. Who here has never made a mistake in math? It's okay. You just have to correct it. All right, how do we correct this? What we want is if x is 2, no, if x is 2, we want it to be what? 3. Okay, thank you. I know there's a 3 up there somewhere. Thank you. Okay. Any other questions? All right. All right. Well, let's clean up the board for a second. So we have a definition for continuous at a point. We have 2 more definitions, and they're both pretty easy. First is continuous. Continue on an interval. Everyone remember intervals? Intervals can be open, like, I don't know. That means I'm interested in all the points between 1 and 3, right? Or they can be closed, which we write this way. I don't know. In which case we want points between or equal to. Can everybody see down this far? I'm not quite sure. Okay. So what is continuous on an interval? Continuous on an interval is continuous if you're continuous at all the points on the interval. You should write that. F is continuous on an interval. I'll just say A comma B, if and only if for all x member of the interval F is continuous. Well, let's make this C. Continuous at C. Now, if you're really paying really close attention to something I don't want you to pay too close attention to, you might go, well, wait a minute. What happens if this is a closed interval? What happens to the endpoints? The endpoints don't have a limit, right? You have to be able to come from both sides. They do have a one-sided limit. And so we have this idea again, just keep it fuzzy, it's not important. There's like one-sided continuity, right? If you have a right-hand limit going this way, and I guess you would say the limit as x approaches a from the right side of f of x equals f of a. So you'd have right-handed continuity, and vice versa, B from the other direction. I don't want you to worry about it. I'm just saying it's, we're glossing over it because it's not going to be important. Okay, so so now at this point it's going to be really useful to realize that there's a lot of continuous functions we know already. In fact, almost every function you've ever dealt with is a continuous function. Almost. Okay? So let's start with polynomials. Polynomial function is a function that kind of looks like this. A to the n, x to the n, plus minus 1, x 1 plus all the way down to a sub 1, x plus a sub 0. Guaranteed continuous. Oh, you know what? I'm sorry. I skipped a step. A continuous function. I'm going to need this. Continuous function is point continuous on its domain. So the domain of a polynomial is all real numbers. So polynomials are continuous everywhere. Okay. Absolute value functions. So I say f of x equals absolute value of x minus 1. Now, what does the graph of that look like? Well, at 1, we have kind of a sharp change in where the function is going. It's going to be continuous on these straight lines everywhere. They're like a polynomial. So this is the only point that's we have to worry about, but sure enough, the limit from either direction is the same. So it's continuous at that point. So absolute value functions are continuous everywhere. Root functions. Well, just look at the obvious easy one. X, square root of x. Well, what's the domain of this function? Domain. Say again? X greater than or equal to 0? Yeah, that's its domain, right? And it kind of looks like this. Kind of looks continuous everywhere, except what about here? Well, there we run into that, right-handed continuity. So it's we call it continuous at that point. It's continuous everywhere. I'm a little concerned when I said, what's its domain, and I got blank looks. I hope it's just early in the morning. If you don't remember about domains and ranges, pre-calc, come see me when you have a chance. We can clear that up. Okay. have a nice long list here of stuff. These are all continuous. They're all nice functions. Exponential functions. So f of x equals, you just say 10 to the x. Well, exponential functions like this, at least, they're going to go through 1. They're going to go up very quickly, but no matter how far out you get, you've got a function, and it's kind of smooth. As you get down into negative exponents, you're going to get closer and closer to 0, but you'll never reach 0. Exponential functions are continuous everywhere. The book brings this up. I'm not sure if we need to discuss it. With a function like this, you have a straight line here. It gets closer and closer to it. What do we have a name for this particular line here? It happens to be the axis, but everyone know the name we give this type of line? Yes?
Asymptote?
Called an asymptote. For one extra point, what kind of asymptote? Yes? Well, the range here it's the bottom of the range. Yeah. But there's a name, there's a prefix we put on asymptote. It's horizontal, right? You can have vertical asymptotes. We've kind of looked at a few functions that have those. And it's also possible to have, you could have a function that gets closer and closer to some line that isn't horizontal or vertical. It's still an asymptote. Okay. Logarithmic functions. These are inverse functions, an exponential function, and there's an associated logarithmic function. So I'll just use f of x equals log to the base 10. I didn't write that properly. Log to the base 10 of x. Now, I have my exponential function here. I want to graph my log function, which is an inverse function. There's a trick. Does anyone know the trick? Real easy trick. Whenever you have a function and you want to draw its inverse, do you know how to do that?
I feel like rotate the paper, but I don't, or like turn it, but I don't really remember.
Well,
Exactly. Kind of
you got to rotate the blackboard, right?
Yeah, exactly.
Okay. You draw the line y equals x, and you take it and you rotate it around that. So you're going to have a point here. I'm not the best graph artist here, but there we go. Oh, and by the way, this has now a vertical asymptote. Now, the domain of this, what's the domain of this? Well, you can't take the log of 0. But you can take the log of anything bigger than 0. And what's the other side of this? Infinity, yeah. Well, this is an open, see now we can see what is an open interval. There's no number way out there called infinity. Every number, no matter how big, is in this interval. And it's continuous on all those numbers. All right. We're not done with this list. there's still a few more functions we know about that are continuous functions. Rational functions. So a rational function is a function which consists of two polynomials, p of x and q of x. Now wait a minute. If q of x is 0, function isn't defined, right? But if it's 0, it's not in the domain of the function. So rational functions are continuous functions. They're continuous everywhere on their domain. They're not continuous on the entire real line necessarily. If q of x is ever 0, then you're going to have a hole in it. But okay, now we have to. We're going to look at the trig functions. And we're going to break it down a little here. Sine and cosine, most definitely, right? They just kind of go off their. Sometimes the word I need is just like right there, and it just jumps out of my head. I want to say repetitive, but that's not the right word. What's the word to describe a sine and a cosine? What kind of function is it? Periodic. Oh, that's the word. It jumped out of my head. I don't know where it went. Thank you. Okay. Now when we look at the tangent function, right, you should know what the tangent function looks like. Kind of goes like this. It's got some asymptotes. But these points here, like, what point is that? Pi over 2, and then 3 pi over 2. Those numbers are periodic. They're not in its domain. It's undefined there. So, tangent function, cotangent, cosecant and secant, which will also have these vertical asymptotes. They're all continuous everywhere. They're continuous functions. And lastly, the inverse tangent, inverse trig functions. Well, in the case of a sine and cosine, we're going to have to limit its domain to make it an inverse. So, I guess I could do my trick where that worked. So on this, for sine and cosine, on the domain you happen to pick for them, they're continuous everywhere. Tangents, I guess in a way a little, you have to limit it. You don't have to limit its domain, but you get something like this. Okay, so these are all, that means it's time for a break. Why don't we take a breather for a few minutes? Use the restroom. All right. Just leave that here for now. Okay, so we're gonna do a real basic, basic problem. We want to show that f of x equal to 1 minus square root of 1 minus x squared is continuous on the interval -1, 1. So, how do we do that? Well, we want to pick some a, any old a on that interval. I don't like competing with bells. Oh, okay, I guess that must be, oh. Thought occurred to me, is that automatic? Or do they have a bell ringer? Makes life easier. You seen the Hunchback of Notre Dame? That great scene where he's like pulling on the bell. Okay. Where were we? So we have some a on that interval, and we want to show that the limit as x approaches a of f of x equals f of a. I didn't pick a, so if it's true for all of a, then it's continuous on that interval. So, okay, that's the limit as x approaches a, 1 minus the square root of 1 minus x squared. So we want to evaluate that. Well, we have some limit laws or limit rules. You know that that's equal to the limit as x approaches a of 1 minus the limit as x approaches a of negative square root of 1 minus x squared. Well, no, we don't need a minus there. Well, that's 1, right? And that's the limit as x approaches a of that's the square root of the limit as x approaches a of 1 minus x squared. And that's 1 minus square root of the limit as x approaches a of 1 minus the limit as x approaches a of x squared. Of course, if you kind of know your limit laws, you don't have to write all this out. You can just kind of go, oh yeah, that's all going to be there. 1 minus the square root of 1 minus. Now what's the limit as x approaches a of x squared? Well, we had that in last class. It's a squared. But this, of course, is f of a. It kind of works. I mean, that's this. You're either looking at this and going, "What the hell? That's so obvious," or "It's so obvious I don't get it." Yeah, maybe. That's it. We're just using our limit rules, and showing that this is the case, and that tells us it's continuous. Okay. I think I'm just going to erase this. Start here. We have a limit law that goes like this. The limit as x approaches a of k times f of x. You can think of this as some function, k times f of x. That's just going to be k times the limit x minus a f of x. It's one of our limit rules or limit laws. You can take constants in and out. Well, we're going to extend that to something with continuity. If f of x is continuous, you could kind of insert whichever of these three you want at a point, on an interval, or a function. It's the same argument. Then kf of x is continuous. Well, how do we know that? We know the limit. If f of x is continuous, then we know that the limit as x approaches a of f of x equals f of a. We can multiply both sides by k. And using our limit law, we can just bring the k inside, and we have the limit as x approaches a of k f of x is equal to k f of a. So k f of x is continuous because f of x is continuous. That's just a direct consequence of our limit law. Okay, well that's nice to know. I'm gonna number this 0 because we have some other laws of continuity that are going to be useful. If f and g are continuous, f plus g, I'm not always sure what kind of notation people are used to. I could write this as f of x plus g of x, or I could write this as f plus g of x. These all mean the same thing. I'm just taking at each point f at that point, g at that point, and adding them together and creating a new function. So this function, if f and g are continuous, these are continuous. Likewise, f times g. Now you want to be careful here. This nice little dot, or I want to use this, or I just want to write it this way. I mean the same thing. The function at each point multiplied together. F and g are continuous. This is continuous. I want to stipulate this is not the same thing. Right? Or we could put x here. This is the composition of functions, like f of g of x, which we will see a lot in this class. You just want to be careful that you don't confuse them. I'm just going to throw this in. I'm going to sneak it in here. F plus or minus. Right? I mean, if you think about it, k could be minus 1, and it's the same thing. F over g, f of x over g of x, this new function, is continuous where g of x is not equal to 0. Well, that makes sense. You can't have it continuous if g is 0. So these are all continuous. That's going to be useful. And finally, well, here it comes. F of g is going to be continuous. Composition of a continuous function with another continuous function is continuous. The proof of all these, we're not going to do these proofs, are all, we just apply the limit laws. Right. If you're interested, I think the book does some of these, but again, it's not going to be important for where we're going. All right. I think it's time to make room over here. All right, so here's an example problem. We want to find the limit as x approaches 2 of x cubed plus 2x squared minus 1 over 5 minus 3x. Why don't you try that? Take a minute. If you have paper, or if you can do it in your head. Question?
I'm just looking at that here. Shouldn't that be negative 2? No, that's first negative 2.
Oh my. Thank you. I don't think it'll matter. We'll just get a different answer. Which would you prefer?
I don't know.
Oh, come on. Change or keep it? Flip a coin.
Keep it.
Okay, let's keep it. I hope I didn't upset you at all, because I want to encourage people, people should speak up. Oh, while you're doing that, I want to preserve my battery here. Yeah. All right. Someone have an idea about this? Do not get intimidated by the possibility it looks really easy. Some of these things are really easy, but you have to kind of see through the obviousness of it, to Well, what do we know about the domain of this rational function? Let me rephrase that. What do we know about the continuity of this function? It's continuous on its domain, right? So what's its domain? Well, by default, it's going to be all real numbers minus where it's 0. Okay, 5 minus 3x equals 0, minus 3x equals minus 5x equals 5/3. So not equal to 5/3. Is 2 equal to 5/3? No. So it's continuous everywhere, which means the limit, right, is going to be equal to the function at 2. So we can just plug in 2, right? So 2 cubed is 8, plus 2 times 4 is 8, minus 1. And 5 minus 6, right? So we get 7 over minus 1, or minus 7. Unless I made a mistake. Okay, once you kind of put 2 and 2 together here with, the continuity, it's easy. Or maybe it looks obvious without that. All right, we're going to try one more here. Okay, let's find the limit as x approaches pi of sine of x over 2 plus cosine of x. Yes? I think what I'm going to do is I'm going to bring in some chocolate truffles. When someone catches me with a stupid mistake like that, they're going to get a truffle. Does that sound all right? Okay, you've earned one. Who else earned one here? I forget. Oh, didn't you earn one? Remind me next class. I'll try and bring in the truffles. All right. What about this? Well, what's the domain? Well, it's not a polynomial function. It's kind of a rational function, except we've got trig functions in here. What do you suppose the domain of that is? Well, it's going to be wherever the denominator isn't 0. Where's the denominator 0? That's an easier question. Okay. Okay. Insert commercial here. If you are a little confused by cosine or sine, come to office hours. We'll talk about it. Right? Cosine goes between -1 and 1. -1 and 1 plus 2 is always positive. It's never 0. So this is continuous. The domain is everywhere. It's continuous everywhere. So all we have to do is find out, this is f of x. You have to find out what f of pi is. We, of course, are using radians. So what's the sine of pi? Ooh, yes.
0.
Yes. And we know this is not 0, so we don't even care, right? It's just 0. All right. I'm going to let continuity settle in for a minute. Oh, no, I'm not. Yeah, I'm going to let it set in for a minute. There's a little bit more to be said here. We're going to be using continuity as a precondition on what we're going to be doing next, which is derivatives. But there's a few useful things we can say about continuity all by itself. We're going to take some continuous function. I'm just going to draw a picture. And we have 2 points on this function, a and b. And these, of course, have evaluated at, we have the function evaluated at a and the function evaluated at b. We want to pick some value here. Some f of x between f of b and f of a. We're going to pick a particular value. We could call it k. Let me just use k. And we have a useful and important theorem called the intermediate value theorem. Says that if f is continuous on AB, and we pick some value between f of a and f of b, then there must exist at least one c such that f of c equals k. In other words, here's k. There has to be some c here so that the function at c is k. And the thing to draw from this is that a continuous function is going to go through all the values in the range, right? So if I had some function, let's say, I'm just going to write y equals x cubed. Or x cubed. The range for x, for this function is what? The range for f of x equals x cubed. What values does the function take on? Well, it takes on all of them. So we know that if I pick some value, I can always find an x that that's true. All right. Now, clearly, if this was not a continuous function, this falls apart. We can pick points here that our function misses. Okay, let's do I'm going to do a simple problem that will show the value of this. We're going to take an equation, 4x cubed minus 6x squared plus 3x minus 2 equals 0. It's a third degree polynomial. You might have had a little experience solving these. Sometimes they're easy, you can factor them. Sometimes you can't really. Does anyone know about the solution to a cubic equation? Anyone know? Like everybody knows that if you have I digress for a minute on polynomial equations. You have an equation ax squared plus bx plus c equals 0. We all know the formula to this, right? Okay. I accept if you shake your head up and down, and not everybody's shaking their head. Okay, more people are shaking their head. Okay. It's the quadratic formula, right? We all, like you go to bed at night and you say your prayers and then you say the quadratic formula, right? Everybody does that, right? What about a cubic? Does anybody know about formula for the cubic? No, okay. That's a whole interesting history lesson. We're not going to go into it. There is a formula. In the 1700s, they were searching for it. Like people in the Middle East knew this probably in the Middle Ages. That's where math moved. When the dark ages of Europe moved to the Middle East. They knew the answer to this. But this they were working on in the 1700s, and it was almost like there was a contest who would find it. And it was a mathematician, I think it was Cardon, who he got halfway there. He solved a simplified version of this, but I think it was, 1750, 1780, somewhere. They found the formula, and quickly after they found the formula for the quartic, x to the fourth, as a formula. They're really ugly. You should look it up, and then you'll know why they didn't teach it to you in high school. And so what would you do if you got the quadratic, the cubic, the quartic? You're going to look for the quintic formula, right? Well, he spent about 200 years looking for the quintic and couldn't find it. And finally, the late 1800s, they found out why. And if you become a math major, which I know not all of it's not high on all of your list, you'll take a whole course that it's not about that, but it was motivated by that quest. So, okay. Big digression, no point in this. Okay. We want to see that there's a solution to this. We don't care what the solution is. We just want to know that there's a solution on the interval 1 to 2. Well, how are we going to do that? Using our intermediate value theorem, which I unfortunately erased. Well, let's look at f of 1 and f of 2. I'm sorry, I didn't say that. No, I did say that, right? So let's make this f of x. Let's find f of 1 and f of 2. So 4 minus 6 minus 2 plus 3 is 1, minus 2 is minus 1. F of 2 is 8 times 4 is 32 minus 24 plus 6 minus 2. Well, add it up, but you can see right away it's some positive number, right? That's all we need to know. We'll just call it K. Well, I want to know if there is a solution here, a value of f of x that's equal to 0. Right? I want well, the intermediate value theorem tells me that since 0 is between minus 1 and whatever that positive number is, there has to be some c such that f of c equals 0. I don't even care what the solution is. I just want to know that it exists. Maybe I want to find that out before I go looking for it. That's possible. Okay. So there's a use of the intermediate value theorem. And we have one more related theorem called the maximum minimum theorem. It says that if you have some continuous function on some interval, I'm worried about this theorem here. Yeah. Specifically a closed interval. No open intervals. That there's a value, f of x equals m, where m is greater than or equal to f of x for all x in the domain. And there is a value of f of x equals small m, where m is less than or equal to f of x for all x in the domain. That is to say, if you have a closed interval, the function will take on a maximum and a minimum somewhere on that function. Now it could be at the endpoints. It could be at A or B. Now, it's important to note this is not true for an open interval. And we have a real simple example here. If we look at the tangent of x on the interval negative pi over 2 to pi over 2, what's the function going to do? On this interval, it's going to get as large as you want or as small as you want. There's no values, big M and little m. Okay. Okay, any questions? I think we're good for today. It's a little early. You can come and ask me questions, or you are free to go.